Hi, my name is Linnea.
I'm Bezia.
And I'm Linnea, and this is episode number 27 of the Lemma Journal Club.
What is the Lemma Journal Club?
The Lemma Journal Club is the show where we read every paper to tell you if you need to read it. You probably do.
We have a terrific paper for you today. We are talking about a paper titled Hunting for Maxwell's Dæmon in the Wild. It's an archive paper, so a preprint put out in 15th of April, 2025 by, among many others, John Bechhoefer. Not right. It definitely doesn't have the Hebrew CH in it. And David Sivak. These are people at Simon Fraser University in Vancouver, Canada. Linnea and I both recently independently went to Simon Fraser University and talked to these people. And so this work was on my mind. But first, I just want to put a little note on last week. I was not around. Oh, my notes are very weird here.
Oh, I'm sorry. I had altered your notes.
Why did you alter my notes?
Well,
They're my notes. It says Bez Notes. Make your own notes.
I wanted to be able to read your Bez notes.
What do you mean you wanted to read my... They're for me. I say them to you. You don't read them ahead of time. Otherwise, why are we talking about them?
Well, last week I read some of your notes on...
Yeah, that I did appreciate.
So that's what I based it off of.
So last week, I was not here for this podcast, and instead Megan recorded it with you, and I got to listen to the podcast as one of our audience members. Mm-hmm. The other thing that I did not realize, I think until yesterday, is that episode came out on April 1st. And you guys at no point explain why I have been removed and why this other person is talking. Or I don't even know if you introduced Megan at the beginning of that episode.
Well, she introduces herself.
Okay. So it could have been taken by listeners as an April Fool's joke.
Sure.
Which I just wanted to clarify. It was not intended as an April Fool's joke.
No, we did not record it on April 1st, so it didn't even cross my mind.
Yeah, it never crossed either of our minds. I didn't put it together until yesterday. And then I realized, I bet people think that we did the Megan thing as an April Fool's joke, where we just completely cut me out of the podcast and put somebody else in.
Yeah, sure. Let's say that. No, I just wanted to start the episode and... Yeah, hadn't planned ahead enough to have an intro for Megan. So
you guys did a genetics paper last week, which I think is really outside the boundaries of what I would still call biophysics. That is now a biology episode.
Megan did ask if we had read any other genetics papers for this.
Which
club.
We have, and you guys found the one that we had done before, which was the ant one, which also is like not a biophysics paper. This paper is on the other side of the spectrum. This is such a physics paper that it's almost not a biophysics paper. I would put this squarely as a biophysics paper, but I talked to somebody at SFU, a quantum mechanics experimentalist, who felt that this work is not biophysics, that this work is statistical mechanics or statistical physics, and that it really is separate from biophysics. And I think that there's a reasonable argument.
Yeah, if you're going to separate out statistical physics from biophysics, which I think is murky, but then this would be a separate field. Yeah. So, Bez, why did you pick this paper?
So I picked this paper because we were recently at Simon Fraser University, and I have a bone to pick with statistical physics, how it is taught, how it is talked about, and how it is measured, or more commonly, how it is not measured. In this case, I talked to a physics audience about my thoughts of like, hey, KBT units are kind of weird. They kind of presuppose the answer. Temperature is or isn't a variable, and that's not clear when you're using these KBT units. And I prefer to use units of joules. And I talked about that I really want to make measurements in units, and I didn't give my whole energy spiel, which is good because these people have a lot of opinions about energy as well that are different from my opinions. And they've clearly thought about this very hard for much longer than I have, which doesn't mean that they're right, but does mean that I should listen carefully. It was fun to talk to people. Particularly, it was fun to talk to John, who I very quickly realized had thought very deeply about this. And I wanted to go through a paper to see how they were thinking about this. And so I'll just say, like, right off the bat, one of the things that I frequently say is that I really hate discussions about information. That I feel like when you use the word information, information is kind of inherently unitless, right? What would you say the units of information are?
Yeah, I don't know. And this is where, I don't know if this is linear with how you're trying to go, but so I talked to John about this work, and this is where I got hung up, was at the information level. And so what is considered information? And I think of information as 0 and 1s in a computer. And obviously that's not what you mean when you're talking about a Kinesin motor. And so what does it mean to be storing information in a biophysics setting? And so we spent a long time just considering what do they mean by information?
Yeah. And so my frequent bone that I pick here is, hey, I'm getting forced to think really hard about something that a theorist came up with. That's not how I want this to go, right? I want to be an experimentalist. I'm making measurements. I'm working really hard to make measurements. And the big thing about making measurements is trying to make a measurement that's not relative to itself, but relative to something else so that you can say that it has units. That's the blood and sweat of a measurement. It's easy to make something relative to itself. It's really hard to make something relative to something else. You look through my work, it's almost all relative to itself, right? Because it's so hard to do. When a theorist starts to say, well, if you change the colloids so that half of them are red and half of them are green, then a colorblind person will say that there's more degrees of or less degrees of entropy than a person who can see color. And that's a real thing. And we're going to quantify that as information. And I just flip the table and I say, look, you're so far away from how my work works, and I need you to meet me, not the other way around. And so I was quite quick when they started talking about information to say, I don't want to think about information, and just to reject the concept. And I think that was incorrect, that they had versions of information that one could think about.
Yeah. I mean, the colloid example that they discuss in this paper is what John talked about to teach me what he meant by information here.
Right. But I do think it's important to say what are the units of information.
Okay.
And so I just want to take these equations 2a and 2b. Equations 2a and 2b, they say sigma dot, right? So sigma dot is the time derivative of entropy, but instead of saying S, they've written a sigma to make it a unitless entropy. Okay, I'm not happy about this, but you got to meet them where they are. It's their paper.
Yeah.
So it's the time derivative of a unitless entropy, and they set that equal to the heat flow. So it's Q dot, which would have units of joules per second, of kBT over second, but they've multiplied it by beta to make it unitless.
Yeah.
Because they're going to make all their equations unitless.
Entropy would also have units of, entropy flow would also have units of kBT per second?
Entropy flow would have units of joules per temperature per second, because entropy, a Boltzmann is a joules per temperature thing.
So beta is going to have units.
Beta is 1 over kBT.
Okay.
And it's perfectly canceling out the kBT of the heat.
Yeah.
So that all that remains is the first term has units of 1 over second, the second term has units of 1 over second, and the information dot has units of 1 over second.
Right.
But let's say that we try to shove units back in here, which is not 100% defined to me. And this is my problem with information, is that I have to measure information. I can measure it as bits or nits or bytes or whatever, but that's not a unit. And so I think that one way I can cleanly put units back in this is I can say, look, the entropy has nothing multiplied by it, right? And I know that entropy should have units of Boltzmann or joules per unit temperature. The information also has nothing multiplied by it. So I'm going to treat information as a form of entropy.
Sure.
It has the same units of joules per unit temperature or as Boltzmanns.
Okay.
And then here's my proposal because David and John had really fast ways to fast talk what information was going to be and what it means in the context of two thermal baths. And I think they're 100% correct, but they've just been thinking about it for so long that it's sometimes hard to keep up. For me, it's going to be if you multiply information by Boltzmanns, that's your physical unit. So now I'll let you follow along the information in bits and bytes, and you multiply by Boltzmanns at the end. And if you're following it along correctly, we'll see if we meet up at the end measurement or not. But that's the goal.
Yeah, so I mean, it seems like a decent definition for the units of entropy. I mean, for the units of information, in that entropy is also feels impossible to measure.
Yeah.
And so...
But it's not strictly impossible to measure. So like one example that I always give to people is the sun. You can do a pretty good job of making a box around the sun and saying, I understand the nuclear processes that are happening in the sun, and I understand the number of particles and the rates at which things are happening. And so I can relatively well put a number on the entropy production rate of the sun in Boltzmann's. And that's a pretty solid measurement. And so in general, when you have a pretty solid, pretty isolated system that's just doing something that's pretty well physically described, and you're willing to put a box on it that's the right size, because a lot of this is like, where am I willing to draw my box? Then you can start to get a good definition of entropy. The second thing here then is that we're quite comfortable talking about potentials and derivatives of potentials, and sometimes, floating potentials like magnetic potentials as a real physical thing, that the floating point does matter, even though it's more or less impossible to measure.
Yeah.
Right? Entropy can be the same kind of thing. You say, I don't know where we are floating. Heck, I don't even know to a scaling factor, but I'm not going to stop measuring it, just like I'm not going to stop measuring potentials. And that's kind of my argument or my two-pronged argument. It's my little fork for why we should really be trying to make measurements of entropy production in Boltzmann's per second.
Yeah. Well, so does this then apply in your mind out to information, that we should also be trying to make measurements of information in Boltzmann per second?
That is why we read this paper.
Okay.
Yeah. So before reading this paper and before talking to John and David, I would have said absolutely not. Information is a con that has been foisted upon me by the Shannon entropy people. People were like, hey, look, the form of entropy and the form of Shannon entropy mathematically are identical. And therefore, we're going to call them the same thing, entropy. But I screamed at the top of my lungs, one of these things has units and the other thing doesn't have units. What did you just do? Just because two equations look the same, if they've got different units, they're not the same equation. I think people would philosophically disagree with me, but that's my mentality towards life or towards physics. And when people break that, I feel that they aren't doing physics. I often get into ruts with learning about like particle physics because they're very quick to drop units, and I'm very quick to ignore people who are dropping units.
Well, do you draw a distinction between dropping units and making something unitless, like what they've done here?
Right.
Where they're like multiplying it by some shenanigans and then it doesn't have units anymore.
And so what I would say is what I want to do, because I understand why people are dropping units, right? What I want is when you make something unitless, the first equation should have units.
Yeah.
The second equation should make it unitless.
Okay.
At the end of your derivation, give me back the units. Mm-hmm. I understand that it's implicit and easy to do, and for many people it's snap, snap, snap. But again, I really genuinely believe that morally, it is the moral responsibility of a person who is purely doing theory or analytical work to meet the people who are experimentally testing what the physical reality is. That the physical reality people, those are the salt of the earth people. Those are the most important people, and everybody else is helping them. And so you gotta start and end where they are. And when you don't, then I get frustrated.
Okay.
This is all related to physics, to the physical reality of the world. If you're doing mathematics or something, or like if you feel like you're doing mathematics, you are under no moral obligation to meet anyone for anything, right?
Did they end up going back to real units? Because I feel like this paper I found really interesting in that it is a pure theory paper that's thinking very hard about an experimental problem.
Yeah.
And so do they make it? Because I wasn't thinking about this unit stuff as I was reading.
And so essentially no, because they're always multiplying the heat flow by beta.
Okay.
They do have some units throughout, but essentially no. I think I talked to John a little bit that they had hoped to have, my interpretation of what he said, this might be wrong, my interpretation of what they said is that they hoped to have certain experiments that they were not able to get. I feel like it's Canada, so I'm not sure, but there was kind of this undertone that because of Trumpian stuff, people haven't been where they're supposed to be, and so it's been difficult to do some stuff. That might be wrong again. This is Canada. But that they don't have that in the final paper. For the most part, they're comparing their analytical estimator to simulations. They do have some meeting up with experiments from a different paper that maybe is the paper we should have done, actually, because that's also a very interesting paper that does have units of force and velocity. But there's never anything with units of joules in this paper or of Boltzmanns. So to go through what they're thinking about two systems that are coupled. The two systems that are coupled are both vaguely following the rules of thermodynamics, but they're allowed to talk to each other in some way. Because they're allowed to talk to each other in some way, one system or the other can, on its own, break the rules of thermodynamics. It can have the heat production run backwards. And the way that that is happening is the other system is handing it something. So what we would normally think about this for like a two-partition engine running at two effective temperatures or two temperatures, right? The way that one bit of the engine can cheat the laws of thermodynamics is some thermocouple with another place of the engine, and you can have some heat flow from one to the other, and that lets you do cycles that create work and stuff like this. Here, they're saying we're not going to have a thermocouple between the two compartments. We're going to have an information couple. And that's really the key point of like whether or not you're allowed to talk about information. And so the prototypical way that they're describing this is they say we have an optical trap with a colloid. The colloid jiggles back and forth. When it jiggles to the left, we move the optical trap to the left. And so it's got a biased motion.
Like a ratchet, yeah.
It's like a ratchet. The colloid is just undergoing thermal motion. If we were to draw a box right, it's unaware of this like changing potential. The changing potential is this information, quote unquote, that's coming into the system. And you're immediately like, bullshit, you drew the box wrong. The changing information is energy being spent other places. But I think the like key point here is that the change in potential is not coming through like a thermocouple. It's coming through something else. And we're going to call that like an information flow. And that's their key. Like we want to use the word information because we feel that that correctly captures the way that these two systems are coupled to each other. I think that's the proposal.
Yeah. I mean, so it's pretty clear to me, and this is where I got stuck with John too, was like, it's pretty clear to me in the colloid situation where you have an optical trap and you're watching, like you or your computer is watching the colloid jiggle, and you're saying, oh, you're jiggling to the left. And then I'm going to move the optical trap. And that's like, I've seen information, I'm processing it, and now I'm moving. I get more stuck in the next step. So the next experiment they describe wanting to connect to in this paper is the Kinesin motor. And here I see, now I'm like excited, right? Because like, oh yeah, these fluctuations could help the Kinesin do more work with less actual work. But I don't see where the information is there. Who's reading and writing, like who's watching the Kinesin and the fluctuations to see like, oh, now is when I should be taking my power stroke.
Yeah.
And so that's where I get stuck on this word information.
So the system in the Kinesin that they are considering, which I'm not convinced is the correct system to, again, let's just meet them where they are. The Kinesin is a molecular motor. It's walking along a microtubule.
Yeah.
That's system one. The Kinesin is attached to a cargo, a giant colloid that's vibrating with Brownian motion. That's system two. They have a link between them that you might think of as just a simple spring, but we've learned that like the neck linkers of Kinesin have all these biases that when they're pulled in one direction versus the other direction, they change how the Kinesin walks, right? So for instance, you could imagine a situation in which the colloid vibrates forward. The Kinesin is pulled forward, it takes a step, it hydrolyzes an ATP. That ATP locks it into place. That's the ratchet. Then the colloid swings backwards, tries to pull the Kinesin backwards, but the Kinesin is ratcheted forward, so it's unwilling to step back. And so the random vibrations of the cargo plus the ratchet mechanism of the Kinesin create a biased walk in one direction.
Yes, I find this very cool. Where is the information in that process that you just talked about?
Yeah, so then they say, and this is pretty interesting. So one thing that is not an information engine, that is just a normal engine, is if you were to have this optical trap on this vibrating colloid.
And just move it continuously.
And you would just continuously move it. That's just a normal engine, not an information engine. So with the Kinesin, if the cargo is just vibrating randomly, right, that's just a normal engine that's pulling the Kinesin forward. The question is, what if the cargo is not Brownian motion? What if there is some bias in the noise of the motion? What if there is an active gel or something pushing around the cargo in a non-random manner?
Is that what they're saying? I don't think that's quite what they're saying. Because I think they're saying that it's not that the colloid is, those fluctuations matter. It matters what that's what they're measuring in this paper, right? But those fluctuations, I think, are the consequence of a ratchet mechanism on the head.
This is what I thought they were originally saying too. But now we go to the paper and they say, for a wide range of physiological plausible parameter values and for equilibrium thermal fluctuations acting on the cargo, we find that the cargo heat flow is negative, i.e. Kinesin operates as a conventional engine.
Where is this?
This is page 5, bottom left paragraph, third paragraph of section 5. Page 5?
Yeah, I see it.
5?
Okay. Yeah, I see.
Okay. So then they say, motivated by the experimental finding of faster Kinesin operation under non-equilibrium noise. That is, somebody else did a optical trap on a colloid thing where they found the Kinesin walk faster if they made some sort of non-equilibrium
thing, yeah.
And theoretical results showing information flows are required to take advantage of different sources of fluctuations. We modify the cargo dynamics to include non-equilibrium noise.
Okay.
So now we're talking about a colloid not moving Brownian motion, and not just a simple ratchet attached to that, but having some interesting bias in its fluctuations. And that's actually not what I thought they were talking about when I was at SFU. And that's, I think, where we get pretty interesting.
Yeah. Right? Well, this gets back to something we've talked about for almost a decade now, which is noise.
So if you're an experimentalist, every time a theorist gives a talk, they'll have a little parameter, which they say is the noise parameter. And they'll talk a lot about the form of the noise. And all the experimentalists will immediately fall asleep because what are they talking about? Yeah. But I think more recently I've started to wake up. I think you have too.
Yeah, I mean, it's all over the place these days.
Yeah.
And so you have to be like, well, if this many people are interested in it, I guess I should pay attention.
They're changing the form of the noise. And so to some extent, I think you could say, I think that this would be okay to say, you now have your Kinesin operating with equilibrium fluctuations at some temperature T, and your cargo operating at non-equilibrium fluctuations at a different temperature, a T effective, that its temperature was changed by these non-equilibrium fluctuations. And so to some extent, you really do have a normal conventional thermal engine with two separate temperatures.
Why do you say that the Kinesin is at a different temperature?
That's just what they do. I'm not saying that. Well, so you could look at figure 3A, and at the top they'll have a cargo and a motor, and they'll have equilibrium fluctuations T for the motor.
Yeah.
And and that's just what they do. I'm not saying that you have to do that. Okay. I think you can probably do T effective 1 and T effective 2. But
also the Maxwell Dæmon thing works even if T effective equals T. So you can still generate a gradient.
I would guess that's not true.
I mean, I read the introduction here and the Wikipedia article on Maxwell's Dæmons, and my understanding was that you could have T1 equal T2 for your two baths.
Yeah. And
your Dæmon at the little gate is saying, I'm moving fast particles to the right and slow particles to the left.
Right.
And so you're going to generate T2 greater than T1.
Right.
But you start with T1 equals T2.
But I think maybe one way to view this is that when you put the effective information into the equation, and if you are willing to convert what it is doing to an effective temperature, that the way that you get an engine in the universe, period, is one effective temperature and a different effective temperature. And maybe the thing being described here is obviously it is silly to talk about this as temperature 1 and temperature 2. That's the wrong language. So why don't we talk about it as temperature plus information? And that language will be a little bit better for both the theorists and the experimentalists making their measurements. And I think I'm behind that, which is crazy for me to say because I've been against information since graduate stat mech.
But this is what you just said. Let me just make sure I am following our conversation. What you just said, though, is let's drop out information and let's just think about temperature.
I'm saying that one way you could view their results,
and
one way that they couch their results, is drop out information and say that it modifies the second temperature.
Yeah.
Now we can think of this as a normal thermal engine.
Yeah.
And I think that is allowed at some level of coarse graining, which gets to this thing that I think that I would say that this paper is really about, which is they make an estimator. They say, hey, we don't have any experimental measurements of compartment 1 and compartment 2. And we're frustrated. So what if you only get experimental measurements on just compartment 1?
Yeah.
Can we infer what might be happening in compartment 2? And most of their plots are comparing, if we knew both sides compared to we knew one side, how wrong would we be? And they talk about different coarse graining in time. And that's all interesting. What I want to know about coarse graining is coarse graining in many bodies. That we're always talking about one motor, one colloid here. But when I think about motors, I always think about many motors, and that's what I'm generally thinking about. And so I want to know about that level of coarse graining.
Interesting.
If we had 6 motors attached to a cargo, what are things going to look like? Because that's what the experiment often looks like, is you think you've got 1 motor attached to a cargo, but you've got 4 motors attached to cargo, because it's really hard to get motors off of motors experimentally.
I think they would be heartbroken.
To know that.
Yeah.
Yeah.
That these, like...
But theorists, if you're listening, you're almost never looking at 1 motor. You think you're looking at 1 motor, and you're almost never looking at 1 motor.
How true is that? I mean, like in these old school Stephen Block, Joe Howard single Kinesin papers, they that was 1 motor, right? Like you hydrolyze 1 ATP to take an 8 nanometer step. How do you do that with multiple? How do you do that experiment if you haven't isolated a single motor?
I just think that you've put in a bunch of motors on like a gliding assay. And then you're just assuming that when something moves, I mean, we assumed this for years when doing our experiments, that when something moved, it was a single motor. And then it turned out that it wasn't just monomers, it was dimers. Well, okay, everybody knew that, but it wasn't just dimers, it was dimers of dimers. Well, okay, some people knew that. It wasn't just dimers of dimers, it was dimers of dimers of dimers. Okay, nobody knew that, right? And we started to get into like, hey, these guys are really acting as clusters. And so maybe you're right, the Steve Block stuff.
I'm wondering, because like I haven't read those papers in a long time, but I read them, intensely in grad school.
Yeah.
And what got me actually excited about this paper was this used to be something I love to think about, is like these individual motors and how their ability to like generate force.
We're supposed to say at the end, like, what experiment did we want to see here or something? The experiment that they want to see, clearly, is someone please measure the fluctuations of the colloid and the spatial fluctuations of the kinesin.
Yeah.
That doesn't seem hard.
No, they just can't get somebody to do it. I was like, talk to Brandeis. John's going to Brandeis in a little bit. I was like, talk to somebody there, give it to an undergrad. Or somebody in Stephanie's lab, Stephanie McClung, Illinois.
Yeah, I just like neither Stephanie nor Brandeis often attaches kinesin to colloids. And I feel like the colloidal knowledge these days at Brandeis is...
there's Ben Rogers.
Yeah, it's bullshit. There's Ben Rogers.
I think an undergrad could do that between Guillaume and Ben. Anyways, I was like, if you had caught me 5 years ago when I was super into this and thinking about doing it for my postdoc, I absolutely would have jumped on doing this experiment. Because I think it's like, it's an easy experiment, so it's very possible you find nothing, right? For a huge number of reasons, including this, like you're going to have multiple kinesin on 1 colloid, and like how do you interpret those results, and like how do you modify this theory for that? But if you get a signal, that is cool, right? That is just like fundamentally cool that a kinesin motor could be able to like harness the fluctuations of a cell to be able to walk more efficiently.
I have a lot of questions about like the actual way that this works, based off of the fact that we know that the neck linker, that kinesin have like a bias towards walking in one direction or the other direction. If they take a reverse step, they actually turn ADP into ATP, right? Like they can like create ATP by walking backwards, which never happens, but they can do it.
Yeah.
One thing that I'm very concerned about for their estimator is, as far as I can tell, going through this several times, if you had a dead kinesin, that would look very similar from a colloidal motion perspective, where like what they say that you're going to observe is a smaller mean squared displacement. If you have a dead kinesin attached to a cargo, you'd also see that.
Well, they do say they have to normalize this by equation 7, right? They say they have this displacement in equilibrium, And my interpretation of that displacement in equilibrium was the dead motor.
Oh, that's a good interpretation, actually.
They actually
really
said
like
something
that.
pretty interesting, which is instead of, they say by immobilizing the motor or eliminating the chemical potential difference of its fuel, which I thought was a really interesting way to say, like, get rid of
Yeah, okay, so they
ATP.
absolutely do address this. In fact, I highlighted this, but I think I misinterpreted what it meant for some reason. All right, very good. All right, very good.
So I do think that there's like they're using equilibrium in a couple ways in this paper, right? Because there's the cargo and the motor, and you want to correct the equilibrium.
You do see now, after reading this paper, why every other room at SFU has an optical trap in it.
Did this paper arise because every other room at SFU has an optical trap? Or
it is super interesting, right? Like they taught the undergrads how to make optical traps in lab, and now there's just optical traps everywhere.
it does
And I really want to make a course called like building a 2-photon laser and see if like 5-10 years later, we just have hundreds of 2-photon lasers just lying all over the place.
Nancy mentioned a grant, which we can apply to pay for that course.
Ooh, interesting. That would
That's
be
how
cool.
they got the optical traps.
Oh, okay. Very cool.
But it does make me reconsider when Cliff mentioned, you could just build an optical trap and pull on these condensates and do this measurement. And I was like, sure, I could just, that's a tremendous undertaking. And that undergrads aren't doing it.
Yeah.
That I'm just like, I could definitely.
Yeah, it's easy to do. I that night before flying home, I drafted up an optical trap setup in my little program. So I've got a layout in mind now.
Yeah. But it took you going to SFU and talking to these people and seeing the optical traps that they had to do that. Like I've been asking you to do it for 6 weeks, right? And you've
I feel like
kept
this is how
putting
it
it
always
off
goes,
just
that,
because it seems kind of intimidating, right?
Yeah.
And it's not actually when you get down to
This is Daniel
brass tacks.
Needleman will say everything is easy. And he doesn't literally mean everything. But what he means is the main obstacle is thinking that there's some black magic, that there's some niche bit of knowledge, where really all you have to do is start trying to do it and you will do it. And that really stuck with me. And yeah, it's true for optical trap. It's true for each thing.
Yeah. I have a confession about this paper and my reading of it,
Okay.
which is that I didn't really look at the figures.
I think the figures do a decent job actually laying out their argument.
Okay. I just I feel like John did an incredible job. We were driving to dinner and he did an incredible job of just giving me verbally this paper.
Okay.
And so I was reading it, I was reading the text and I was like, oh yeah, Maxwell Dæmon. We talked about that. We talked about these different experiments and following along that way. And then I was like, I
think
guess
the
I should go back to
most
these
interesting
figures.
figure is figure 2, which is a numerical simulation where they know both sides of the answer. That's the dashed line in figure 2. That's the true heat versus their numerical simulation of their estimator. Because again, this paper is about this estimator thing.
Yeah.
We're talking about a lot of things adjacent to this paper, but it's really about their complaint that they can only get one side of the equation.
Yeah.
So how good can they do from that currently? And in the top case, that's the top case of a standard engine. That's just a colloidal engine. And as they increase the time step of the estimator, it gets closer and closer. And there's always some negative heat flow. In B, they now have this, he called it a Szilard engine, which, man, I just love anything named after Szilard, right? Just can I just study things that Szilard did for my whole career? In the Szilard engine, the estimator even switches signs from a negative heat flow to a positive heat flow, depending on the time step.
Yeah.
Because this cheat that they're doing of this kind of quasi-static approach is super fragile, right? That they're doing quite a big cheat. And to make it work, they need to get really to tiny time steps for this to work.
Yeah. Experimentally, that does seem like the place where I was like, I don't know how possible this is. And again, going back to units of what is the time scale you really need to be able to measure these MSDs on.
Yeah, and so I think that you need good separation of each time scale. And the most important thing here is that you'll need good separation of the colloidal thermal motion time scales from the motor stepping time scales.
Yeah.
And I am afraid that the motor stepping time scales really, instead of being motor stepping time scales, should be motor wiggling time scales. And if that's the case,
Then they're the same.
then they're going to be the same. Yeah. And so that does I was thinking about this on the plane ride home, that an interesting thing about this motor ratchet, because I'm not quite sure, is the information coming from the colloid, which is undergoing this non-equilibrium thermal bath, or is it coming from the motor ratchet? I don't really have it in my mind of which way it is. But from the motor ratchet perspective, the ATP use is crazy high, 10 to the negative 19 joules, or they would say 20 kBT, but then I'd be like, is T a free parameter here? The amount of energy that you pay for a bit of information is crazy high. And if you're not carrying a cargo, I did like a back of the envelope calculation. If you're not carrying a cargo, then it's about 6 orders of magnitude more than the work you've done for if a kinesin is just moving along, that you've done like 10 to the negative 25 joules of work for just moving a kinesin along a microtubule, and all it's doing is moving itself. And it's still paying 10 to the negative 19 joules in information for each time it lays down its ratchet. That you can't ever use up a 10th or a 100th of an ATP. You always have to use up a whole ATP.
But I get turned around by what you mean by information here. Like what?
Yeah,
is
so
the information is that it knows which direction to walk? That's not right, because that's a protein interaction thing.
Yeah. This is why I don't like the use of the word information. I don't like that it's unitless. But let's see. There's a heat flow, which is the release of the ATP. There's an entropy change, which I also don't understand in the case of the kinesin moving down the microtubule, because what entropically changed here? That's why I want many kinesin, or like a many body thing, so I can think about entropy better, I think. And then, like, I think the way that I'm supposed to think about the information for the kinesin colloid system is that the neck linker
will only let you walk if it's not under tension or something.
Oh, I wasn't going to say that. I was going to say that the neck linker is like a force between the kinesin and the cargo. And the neck linker is like the analog of the optical traps position. So it's like the angle of the neck linker is the information, or the change of the angle of the neck linker is the information, just like the change of the optical traps position.
Well, but the change of the optical traps position is not the information.
Is that true?
I mean, I don't know, but in my mind, the information is that I know that the colloid has moved up, and so I move my potential.
How is that different from the change in the optical traps position is the information? I guess you're saying it's in response to something, which is important. You're right. Yeah. So
it's the position, because you could equally say, like, it's the position of the colloid that's the information, right?
The kinesin neck linker,
or the DT of the colloid
changing its force in response to the colloid's position would be the information flow. I wonder if we have that right. I don't know. This is why I like scream bloody murder when I hear the word information, is it immediately starts to hide to me what is the physical picture I should be drawing. But I do think that I'm going to start...
the idea that you, like, the thing that makes me want to think about it more is the idea that this could allow a motor to, like, respond to different kinds of noise, right?
Yeah.
And have different behaviors in a non-equilibrium bath versus in an equilibrium bath.
And I think, to me, what excites me is that this is a way to start to talk about out of equilibrium dynamics in a way that I kind of feel is more intelligent, that if I can then do this in a single molecule way and then bring this up into a many molecule kind of system, I'm going to start to write equations that are different than the kinds of equations I was writing before. And that kind of excites me. But God damn it, give me the information in units. And like really every time give me a diagram that shows me exactly what the information is. It's something that I naturally rage against.
If you have this in figure 3A, like put some arrows showing me where you think the DI DT is happening.
That would be great.
That would help me just like wrap my head around this.
So great paper.
Yeah, great paper.
A lot of fun. Fun to think about physics again.
Did you read the Wikipedia article about Maxwell's demons?
I did not, actually. I knew the game in general.
Okay. I read a little bit about them, and one of the things I learned is that Maxwell didn't call them demons because he was too religious.
I'm not sure how I feel about the demon naming, actually. I made a
person who eventually named it said, like, when it was named demon. It was actually supposed to be named Dæmon.
Yeah, Dæmon I would like a lot better. If
And it just got like misnamed throughout history.
I would like people to write Dæmon, put it on like computer science, a Daemon.
And you want to be daemonic instead of demonic.
Yeah, so that because they talk about demonic behavior in Maxwell's Dæmon. And I am concerned constantly as an American how certain terms will play if you come in front of Congress to justify your funding. And I feel like saying that you're studying demonic behavior will likely not go down well with the ultra-Orthodox Christians in American Congress. I'm not sure. I don't actually know that. But then again, it might play really well with like video game people, which is this younger generation. So actually it might work out for you. People are like, ooh, they're studying demonic behavior in Maxwell's Dæmon. Let's give them some money, right? But I feel like you could still capture the video game people and not piss off the Christian people if you just say Dæmon instead of demon. It's a small enough change that no one will care. You can even use the AE that's a single character.
Yeah, that's what it's supposed to be.
I
mean, I think the demon stuck because it's a paradox, right? Where you're like it seems like it's impossible.
It's not a very good paradox, though. It's not exactly like a quantum bomb paradox where it's like something that you really like, what is going on here, right?
Well, I think when it was first proposed, people were like, this breaks the second law of thermodynamics, and they didn't have an explanation for it. So anyways, I like the reason why I bring it up is that, well, A, I read it and I thought it was interesting. And then B, is that there's a little bit of whimsy in either demon or Dæmon.
Yeah, I just feel like equal whimsy, Dæmon.
Equal whimsy. And the title of this paper, Hunting for Maxwell's Dæmon in the Wild, right, is a very whimsical title that I think can only be the title of an archive paper.
You think it can't be in a published paper?
I mean, we'll see where they submitted it. I could imagine a few journals that let them keep it.
I mean, this seems like it'll go to PRE or PRR. You don't think you can get away with that in PRE or PRR?
I think in PRE you probably can, but I'm not sure. It depends on your reviewers, I'm sure, too.
Should we say anything about the fact that this is our first archive paper? We've never been against doing preprints. I personally feel that preprints are just as valid as a fully published paper. We just didn't want our first 2 or 3 papers that we ever covered to be preprints. In fact, that's why we didn't do Suliana's mitochondria purling paper. And instead we did, who's the last author on the other?
Wallace Marshall.
We did Wallace Marshall's purling paper because we thought that they were roughly equivalent. And we wanted to start out by doing real papers. But we've never had anything against archive papers. We've just never done them. This doesn't mean that something's not peer-reviewed, but bad news, folks. I really don't think peer review adds anything beneficial to a paper whatsoever, other than like kind of turning something from a nice, like wonderful meal to just kind of like a mush that's been stomped on by other people. That's or it's just the same paper. Those are kind of the two outcomes.
Yeah. I mean, it was a good paper. The thing that's annoying about doing like just on an annoying level, not on a like philosophical level about doing an archive paper is that it could change.
Yeah.
And so like we've read this paper, but have we read the whole work?
Yeah.
We still don't know.
Yeah.
And we won't know until we see this paper come up on our weekly update as fully published. And then we'll have to click on it and check if anything has changed. And that's kind of, like, then should we have just read the full paper? We're never going to do a journal club on the full paper because we've done the archive paper.
Yeah, absolutely.
I'd say that's the only annoying thing.
And there's also like you don't generally have access to experimental videos if they were put up unless the person putting it on the archive has put extra care into having the videos. And if there's code that's supposed to go with it, you generally don't have the code.
But I trust this paper just as much as I trust any published paper. Like these people are putting their reputations on the line in the same way by putting this up on archive as they are when they publish a paper in a peer-reviewed journal. So.
And unlike a peer-reviewed journal, once they realize mistakes that they've made, they can actually fix them on the archive. Whereas a peer-reviewed journal, you're stuck looking at someone's mistakes forever. My major...
I think it's actually David that has a errata on his website.
That's who you were talking about. Okay.
I think so. I mean, we'll edit it out if I'm wrong.
Yeah, that sounded like a really good idea that like
It's all very small things, like this reference was wrong, or like this person has moved, or, this equation should actually be this.
I really want to do that because I know of at least one error that I have in a paper, and you cannot get errors fixed in papers. The journal editors will just not let you do it because they have no mechanism by which to fix small errors other than to say, we've talked about this before, a giant error in which an entire swath of the paper is wrong, and a small thing like, oh, this was supposed to have units of 1/seconds, but here it has units of seconds, right? Are considered the same error as far as like the internet is concerned. And it makes it that there's just like a massive amount of trivial little errors that are never getting fixed online, which kills me.
But yeah, archive, you can just update because you're in total control. Do we want to address any of our outro questions? We've talked about the paper or the experiment we would do if we were to add something to the paper.
For Asya, why in the world were your parents interested?
Yeah, we thought these people were interesting as one side.
I also think that this is like, if I didn't care about giving back to humanity on an immediate time scale, I didn't care about treating disease, and I didn't care about my own reputation or about making money or about being important or about feeling good about the work I'm doing. If I was a monk in the middle of Mongolia, not interacting with other human beings, this is probably what I would spend all of my time thinking about.
Is Kinesin motor walking, or
is what it
means to be entropic?
What energy means in different length scales and different time scales and the exchange of energy. And I would just be thinking about this stuff and be thinking about what does it mean to feed in energy in different ways to one side of a system. Yeah.
I mean, that sounds much more productive in your monk alternate universe than in my monk alternate universe, where out of this paper, I would think about how Kinesin motors walk. Like, it's still a question that really captivates me for reasons that are just historical, right? Of like how I got into like non-equilibrium systems. But I just find it like nobody's really answered it satisfactorily to me, and it matters. Like it really affects all of the subsequent steps in like any active hierarchical system.
In early journal club back at Brandeis, like 4 or 5 papers in a row about how Kinesin walk.
Yeah.
And I think it died with, we got like a rat version of Kinesin 2 that only had one head and like a, somehow an electrostatic little bit that acted as a second fake head, like an anchor, and kind of like bunny hopped around, and then also made a helical motion around the microtubules. And we started talking about to what extent other Kinesin make a helical pattern around microtubules. And I think that was the point where the rest of us were like, this is too difficult. There are too many Kinesin, there are too many walking mechanisms, and everyone's just guessing. I'm out. And we stopped covering these papers. Yeah.
Tyler, Ross, and I used to spend, like, when we were up till 2 a.m. doing our light activated experiments back in early grad school, we would just spend all of our time thinking about if you really did understand these motors to that level, like think about all of the symmetries you could exploit, and like true. All the beautiful systems you could build. If you really understood the molecules that well.
Yeah, that's a great point. And then just some things. We're doing this thing every Monday where we just talk about all the papers that have been published in the past week. It's very helpful for us to be aware what has been published, particularly what our friends are publishing. Nobody watches that.
Yep.
Another thing is I really, really desperately want to do some drafts.
Yeah.
And so with that, we have some big plans that we may or may not get to. And there's a lot of papers that I desperately want to do. John Beresny, Itamar, and Ray's paper, I really want to do. We could do...
I mean, that's an easy pick for next time, I guess.
I think we should do it. We should do Suliana's paper, even though we've kind of already talked about this, and I don't know how much more information there is to learn about that system.
Yeah.
Yeah, and it's an exciting time in science. If you're watching the Monday episodes, you can see that there's a lot of papers out.
For how bleak things are on a funding sense.
Because it's everyone putting out their last hurrahs, right?
Yeah, the paper side is just so strong. And I know there's a huge lag, but like
3 to 4 years from now, there's going to be a dearth of good science.
How are people not excited about science? It's so beyond me.
All right.
Bye.
Bye.